Now we'll begin our next section of the class, and we are taking a little bit of a journey through the history of science up to Isaac Newton. And we've got to understand one important part of this history, which is that one of the most important driving factors in the history of science is the observation of the heavenly bodies. This can't be overestimated. In other words, the ability to see the night sky and to see the planets and the stars and their motions in the heavens has been a key factor in the development of physics and the development of science. And here we have we've got a diagram of the ancient Ptolemaic system. Now, Ptolemy was a Greek, an ancient Greek. He lived around 100 BC, and he recorded the movements of the planets, and the understanding at this time was a geocentric universe, and geo means earth, centric means center, so earth-centered. So you see here in this drawing we've got the earth in the very center of this system, and if the earth is in the center and you graph the movements of the planets in the sky over the course of a year, you get a very strange pattern, which is you get these epicycles. So the planet will appear one night to be in one position, and then it will kind of go backwards and make some kind of crazy orbit and do all these wild things. And what you're really seeing is the interference of the fact that the orbits take different times to go around the sun. But of course they believed the Earth was in the center, so they had to draw the solar system and the movements of the planets as if the Earth was in the center, and you got these crazy, inexplicable epicycles. So again, nothing really happened with this for about 1500 years, but then came along a fellow by the name of Nicholas Copernicus. So we arrive at Isaac Newton, and what did Newton do? Well, he did a lot of stuff, but the main thing that he did was to bring together all the different strands of science that had been brewing for the last 2,000 years before him. So what did he take from Plato? Well, he took the understanding of the reality of the mathematical or the ideal world. In other words, it was very clear to Isaac Newton that the world of equations, the world of mathematical relationships, had a direct connection to the physical world in which we live. And that's what he took from Aristotle, was the importance of observation. And from Galileo and from Kepler, he took this the understanding and really put together for the first time in a completely coherent way the scientific method. And with the understanding that the theories took the form of mathematical relationships. So let's talk about what that means. We all know the story that, we hear that Isaac Newton discovered gravity. If you think about that statement, it sounds a little crazy. In other words, did people not realize that there was something holding them down to the earth before Isaac Newton? It was all of a sudden Newton let everybody know that they were being held down by something. Obviously, that's not the case. So what does it mean that he discovered gravity? We know the story that there's some apple that fell on his head, and we see this little diagram here of an apple about to clock somebody. And all of a sudden, something clicked, and he discovered gravity. Well, what did he discover? What Isaac Newton showed was that a certain mathematical form for gravitation, which we'll learn in class, when applied to the orbits of the planets, gave the exact same result. In other words, using his formula and knowing the location of the planets, he could derive their orbits with his equation. And so what his equation stated is that all matter in the universe attracts all other matter in the universe, and it does so according to an inverse square law. And what that means is it's the force of gravitation between two objects is proportional to 1 over the square of their radius. And okay, you don't need to, if you don't understand what I just said, it's okay, because I'll show you in class, and it will make sense. But the point is, there's a form, a mathematical form, that describes what happens in nature. So that is Newton's theory of universal gravitation. It's literally an equation. But when you take that equation and you figure out what its implications are, you end up with all of the orbits of the planets. It describes perfectly the motions of falling bodies. And so what he shows is that what we experience here on Earth as gravity and what we observe with the motion of falling objects can be described with the same equation that will describe the motion of the planets. So for the first time, there is a theory that takes into itself diverse observations and under one umbrella shows that they are connected and they are really the same phenomenon. And this is a major achievement in the history of science. It's really the first time that it happens. It's the most, the first real profound scientific law that's developed. Now, the other implication that this had was it showed once and for all that the objects that we observe in outer space are subject to the same forces, the same scientific laws, the same type of reality that we have here on Earth. And before Newton, and really according to Aristotle, so for a long time it was held that everything in outer space was, there was no concept of outer space. The heavenly bodies was this other realm, this other sphere, this other type of existence, and the things there were incorruptible. In other words, they were perfect, they were ideal. Well, Galileo observed sunspots, and of course this cost him his eyesight most likely. But when he did so, he saw that, okay, there's something, the sun isn't just a perfect disk. There's something imperfect about it. There's these blots on it. And well, when Newton showed that gravity on Earth was the same thing, the same force that kept the planets in orbit, this showed it that once and for all, okay, the heavens, meaning the things in outer space, are really the same stuff that we have here on Earth. And this was, again, a big blow to the kind of the worldview that existed at that time. So Newton takes into himself contributions from Plato, from Aristotle, from all of the scientific work leading up to him, and really synthesizes it. And he comes up with the laws of motion for the first time, extremely clearly and systematically laid out, with understanding what acceleration is, what force is, and the relationship between the two. We'll learn these things in class. The other thing, he did a lot of work with optics, so that's why I have this picture of a prism here, and it's splitting this beam of white light into its constituent components of color. And it's interesting to know that the reason it does that is because it's actually a cheap prism, meaning that the lower quality optics do that. High quality optics don't do that. You don't want that, what's called chromatic dispersion, happening in your glasses, or everything has a little rainbow around it. And I've got cheap glasses, so I see that most of the time. But in any case, he started to describe optics, and his famous book is the Principia, which is right here. and this is the kind of the beginning or the most fundamental work in the history of physics. So Isaac Newton is the one who really brought all the strands together into one coherent system, and his system is still taught today, and that's what you will be learning in this class, are pieces of Isaac Newton's system of physics. So it's not outdated in the sense that it can be used very accurately. Using Newton's laws alone, you can successfully place an astronaut on the moon. However, there has been a modification to Newton's laws, and this has to do with the work of Albert Einstein. We will not be talking about this today, but we will discuss it in the class. And what Einstein did was essentially the same thing that Newton did, is he found an even more fundamental principle. And so here's the kind of the interesting fact. So even though Newton describes the equation for gravity and uses it successfully to show that show the orbits of the planets and show the trajectory of projectiles and all of these kinds of things, he states very, very clearly he has no idea why gravity happens. And all he does is describe what gravity is, meaning, or describes how gravity behaves. He knows how it works, but not why it works. So, and he's very clear about that. And Albert Einstein goes further and starts to get into the why gravity happens. And we're not going to talk about that right now. So this has been a short history leading up to Isaac Newton. And it's basically Newtonian physics that you'll be working with in this class. It's also known as classical mechanics. So now we'll stop this video, and you can go ahead and look at the next link in the for this week.